Welcome to this A-Level Chemistry multiple choice question walkthrough where I'm going to be looking at the bonding and shapes topic. Download the question from the description, have a go at them yourselves, and then watch my video and see how you got on. Which species contains bonds that have different polarities? Well, you end up with a polar bond when the atoms in that bond are not sharing those electrons equally because one of those elements has a larger electronegativity than the other. That gives rise to what's called a dipole. For instance, in A, nitrogen is bonded to hydrogen, and nitrogen is much more electronegative than hydrogen, so the nitrogen will be more electron rich as a result. However, in A, all four of these bonds are between nitrogen and hydrogen, so whilst they will be polar bonds, overall these bonds are all going to have the same polarity, so A is not the answer. And then if we move on and look at B, we've got the same situation. Chlorine is much more electronegative than carbon, but all four of the bonds are between carbon and chlorine. So whilst those bonds will also be polar, they will have the same polarity. So B again is wrong. C, well, this is the first option where we could have different polarities, and the reason is the central carbon atom is connected to different things. Firstly, we've got three hydrogen atoms. Hydrogen, ever so slightly less electronegative than carbon, but they are about the same. And then the chlorine is much more electronegative than carbon. So the polarity of the carbon to chlorine bond will be the chlorine will be delta minus and the carbon will be delta plus, whereas the other three bonds, if we have to commit, actually they would have the opposite polarity. The hydrogen would be delta plus and the carbon would be delta minus from the point of view of each of those three bonds. So C is the correct answer because we've got these two different polarities in this molecule. If we just double check D, the oxygen is only bonded to hydrogen. Each of those three bonds will have the same polarity, so D is wrong. Which compound contains a coordinate bond? Well, a coordinate bond is formed when one atom in a covalent bond donates both of the electrons into the bond itself. So it isn't one electron from each atom, they both come from one of the atoms in the covalent bond. Looking at each of these in turn, in HF, hydrogen is in group 1 and fluorine is in group 7. They each need one extra electron, so they share one each in a normal covalent bond. And so no coordinate bond in A. In ammonia, NH3, nitrogen is in group 5 and so needs 3 more electrons to fill its outer shell. Hydrogen again needs one extra electron, and so 3 normal covalent bonds form, giving nitrogen its 8 with one lone pair and hydrogen its 2. So again, no coordinate bond here. CHCl3, you've got the central carbon atom with 4 valence electrons. It's going to be bonded to 4 elements around the side, and so those are going to be 4 normal covalent bonds because the hydrogen and each of those 3 chlorines needs one extra electron to fill their respective energy levels. And for the last one, this must be the one that's got the coordinate bond. We've got nitrogen with 4 hydrogen atoms around the outside, and so this is going to be the ammonium ion, and so there'll be a coordinate bond in the ammonium ion itself, because as we saw in B, ammonia normally has one lone pair of electrons. There's an extra hydrogen in that structure, so that hydrogen must have bonded to the nitrogen through a coordinate bond. Overall, that makes the NH4 a 1+ ion because hydrogen, if it's going to form a coordinate bond, can't bring an electron with it itself. So NH4 is 1+, Cl will be 1-, and so ammonium chloride will have coordinate bonding, covalent bonding, and ionic bonding all in one. Which statement about intermolecular forces is not correct? So we're looking for the false statement out of these 4, so we're looking for 3 true statements that we can disregard. First of all, A, intermolecular forces exist between all simple molecules. That's a true statement because you get van der Waals forces, also called temporary dipole-induced dipole forces, in all simple molecules. B, hydrogen bonding occurs between HBr molecules. Well, the tip for remembering whether something contains hydrogen bonding between molecules is to look for a delta positive hydrogen, which we've got, and to look for a fluorine, oxygen or nitrogen with the lone pair. And this doesn't have it, it's got bromine instead. So this is the false statement, which means that this is the correct answer for the question. Just to check the others, hydrogen bonding is the strongest intermolecular force in liquid ethanol, definitely true. Ethanol has got the O to H bond, which will be polar with an electron-deficient hydrogen, and the oxygen with the lone pair. And D, hydrogen bonds occur between the carbonyl and the H to N group in proteins. That's absolutely true, and that's part of what gives them their three-dimensional structure, the existence of these hydrogen bonds. So B is the correct answer. Which one of the following bond polarities is not correct? Well, you get polar bonds when there is a big difference in electronegativity between the two atoms sharing the pair of electrons. And the bigger the difference in electronegativity, the bigger the dipole. And the more electronegative element gets the electron-rich symbol, the delta minus symbol. And so what we need to look for here is the instance where the more electronegative element is actually labelled as delta plus, and therefore being wrong. And so in A, we've got carbon and hydrogen. Now, you're actually taught at A level that these two have got really, really similar electronegativities, so you might not be able to commit here as to whether this is right or wrong. So let's look at the others. In B, the bromine is the more electronegative element, and so this is the wrong answer because the polarity is right. And this is the same again in C, because oxygen is also more electronegative than carbon and is labelled correctly as delta minus. And in D, we've got the exact same scenario again. The more electronegative atom is being labelled as delta minus, and so these three, B, C, D, are all correctly labelled, which means that A must be labelled wrong and therefore be the correct answer to this question. And that is indeed the case. Hydrogen is actually ever so slightly less electronegative than carbon, and so it's the hydrogen that should be actually labelled as delta plus, electron deficient, and the carbon would be the delta minus. So A is the correct answer. Which one of the following molecules is not planar? Well, when we're looking for a planar molecule, our most common examples are linear molecules or trigonal planar molecules. So let's start by looking for those. The way we do this is by looking for the number of outer shell electrons around the central atom. So we start by looking at the group number that this atom is in, because that's the number of valence electrons it has before it starts bonding. Then we look at the number of new elements that are bonded to it. That's the number of valence electrons they will bring to the molecule. So if we look at BF3 as our example, boron is in group 3, so 3 valence electrons. There are 3 fluorine atoms connected to it. That gives us a total of 6. These electrons will go around in pairs, so that means there will be 3 pairs. For BF3, there will therefore be 3 bonding pairs of electrons, and this will therefore be a trigonal planar shape. So this is planar, which means it's the wrong answer. Moving on to NCl3, nitrogen's in group 5, so 5 valence electrons. There are 3 chlorines attached. Add those two numbers together, we get a total of 8 electrons in the outer shell of the nitrogen now. And that means we've got 4 pairs of electrons. 3 of them will be bonding pairs of electrons between the nitrogens and those 3 chlorines, and there will be 1 lone pair of electrons. So this will be a trigonal pyramidal shape, or a trigonal pyramid. This is not planar, very much 3-dimensional, so this is the correct answer. It is not planar. In a test, this is where we'd move on, but just to look at C and D and prove why they are planar, C2H4 is an alkene, and it's a very small alkene, it's ethene, and so around each of those carbon atoms in the double bond, there are 3 clouds of electrons. We treat the double bond as just being a cloud the same way as the other single bonds, and so we've got 3 clouds, so this is going to be trigonal planar around both of those carbon atoms, so the whole molecule will be flat. D is an aldehyde, it is methanal, and that is also going to be flat for the exact same reasons. We've got 3 clouds of electrons around that central carbon atom, and so the trigonal planar shape will once again be the shape this molecule has. Here we're being asked, in which one of the following species is the shape influenced by the presence of 1 or more lone pairs of electrons? To work this out, we're going to look at the number of valence electrons around the central atom in each of these molecules. So to do that, we need to start by looking at the group number of the central atom, because that tells us how many valence electrons that atom brings. Then we look at the number of atoms that the central atom is bonded to. Then we have to account for some charge. This will give us a total number of electrons. We then divide this by 2 to get the total number of electron pairs and compare that to the number of bonds that must be in this molecule. So for instance, if we look at the first one, we can see that there is nitrogen, which is in group 5, so 5 valence electrons. Then hydrogen, there are 2 of them attached to it. And then there is a negative charge, which means that an electron has been gained in this molecule. When we add all of this together, we get 8 electrons in total, which is therefore going to be 4 pairs of electrons. Since there are 2 hydrogen atoms bonded to the nitrogen, that means there will be 2 bonding pairs of electrons, and therefore there will be 2 lone pairs of electrons. They will influence the shape of this molecule. We've got our 4 pairs, which makes us feel like it might be a tetrahedral arrangement. 2 lone pairs forces those bonding pairs closer together, and so we get a V-shaped molecule with a bond angle of 104.5 degrees. That means that A is the correct answer, and so the others are therefore not influenced by lone pairs of electrons. The reason is that NH4 is going to be tetrahedral with no lone pairs. CH3NH3+ is also going to be tetrahedral around each of the atoms of carbon and of nitrogen. And then the last one is cobalt with 6 ammonia around it. That's actually going to be 6 dative covalent bonds around the cobalt atom, and so overall we're going to have an ion. This is called a complex ion, but again, no lone pairs around the cobalt influencing that shape, it's just octahedral. So A was the correct answer. Which of these has a bond angle of 109.5 degrees? Well, you need to know that the bond angle of 109.5 degrees is what you find in a tetrahedral arrangement. And so really what we're being asked to do is find out which one of these has a tetrahedral arrangement. Looking at A, carbon in the form of diamond is a giant covalent structure where each carbon atom in the structure is covalently bonded to 4 others. These 4 bonding pairs of electrons around each carbon atom will be in a tetrahedral arrangement, and so therefore the bond angle will be 109.5, and so A is the correct answer. If we look at the others to see why they're wrong, in graphite, each carbon atom has 3 covalent bonds. These 3 bonding pairs of electrons will be able to get 120 degrees apart from each other. So this will be a flat arrangement of carbon atoms with a bond angle of 120. In C, NH2-, nitrogen is in group 5, so has 5 valence electrons. It's connected to 2 hydrogen atoms, and then there is a negative charge, which means an electron has been gained, which means this will have a total of 8 electrons, therefore 4 pairs of electrons. 2 of those pairs will be bonding pairs between the nitrogen and the hydrogen. The other 2 will be lone pairs, so V-shape. In D, nitrogen, still in group 5, is bonded to 3 hydrogen atoms. There is no charge, so the total electrons is going to be 8. That means 4 pairs of electrons, 3 of which will be bonding pairs because of the nitrogen to hydrogen bond, and then there'll be 1 lone pair. That makes this a trigonal pyramid arrangement with a bond angle of 107 degrees. So to return to the correct answer, in diamond the carbon atoms are arranged in a tetrahedral structure and the bond angle is 109.5 degrees. Which of these substances has permanent dipole-dipole attractions between its molecules? Well, when you're working this out, you're looking for the presence of an atom that is particularly electronegative. So typically we're talking about nitrogen, oxygen, fluorine as being the big 3, followed by chlorine. Now this is tricky because actually all 4 of these molecules have these atoms present, so it can't just simply be that. We're also looking then for whether the molecule as a whole is going to be polar, because a series of dipoles within a molecule can actually cancel each other out if the molecule is symmetrical. So we're looking now for whether the molecule is symmetrical. A is a tetrahedral arrangement. Those 4 dipoles that will be present will cancel each other out. Similarly, in B, this is a flat molecule, and those 4 polar bonds between carbon and fluorine will cancel each other out because they're all in equal and opposite directions. C, which is propanone, is not totally symmetrical insofar as there isn't a counterbalance to the dipole that exists between the carbon and the oxygen, because there is only one dipole in this molecule. And so C is going to be the correct answer, because the electron-rich oxygen will be pulling electrons in one direction, making one half of this molecule slightly negative and the other half slightly positive, and there's nothing to cancel that out. If we look quickly at D, we have a similar situation in that we've got a carbon to oxygen double bond, so electron rich on the oxygen and electron deficient on the carbon. However, there is another one on the opposite side pulling the electrons in the exact opposite direction. So overall, those two dipoles are going to cancel each other out within this linear molecule. So again, C, the correct answer. Which compound has the highest boiling point? Well, the one with the highest boiling point is going to be the one where there is the strongest type of intermolecular force between the molecules, and that strongest force is hydrogen bonding. So really, this is a search for whether there is hydrogen bonding in the molecule. To have hydrogen bonding, you need an electron-deficient hydrogen, and you need a fluorine or oxygen or nitrogen that has got a lone pair that can form that hydrogen bond to the electron-deficient hydrogen. So if we look at butanal, you can see that we've got the oxygen with its lone pair, but there aren't any hydrogens connected to something that is suitably electron withdrawing to make that hydrogen atom electron deficient. So A is wrong. In B, we've got the oxygen again, but this time the oxygen has a hydrogen atom attached to it, which will make that hydrogen electron deficient. And so B can have hydrogen bonding between two butanol molecules. So this is likely to be the correct answer. We just need to double check that C and D don't have hydrogen bonding. In C, but2ene does not have fluorine or oxygen or nitrogen present, so it cannot have hydrogen bonding. In D, 1-fluorobutane does have the fluorine atom that we need, but none of those remaining hydrogen atoms in the molecule are connected to anything other than carbon, so they won't be delta positive, so D will just have the permanent dipole-dipole forces and definitely no hydrogen bonding. So B will be the correct answer. It's got the highest boiling point because it's got these hydrogen bonds between the molecules, which is the strongest type of intermolecular force. Which molecule does not have a permanent dipole? In order for a molecule to have a permanent dipole, there needs to be a bond between two atoms that have got a different electronegativity. And not only that, this needs to be a non-symmetrical molecule. In other words, some molecules that are symmetrical have more than one dipole, and these dipoles are acting in opposite directions, and their effects cancel each other out to give a non-polar molecule overall. In A, we've got the chlorine, which is one of the highly electronegative atoms, and this molecule is non-symmetrical. So this will have a permanent dipole, and it will be a polar molecule. In B, we've got 3 chlorine atoms, and these chlorine atoms will all be in slightly different directions to each other, but there aren't 4 of them in this tetrahedral arrangement, so they don't cancel each other out precisely, and so this will be a polar molecule with one area being slightly negative and the other being slightly positive. In C, we have 4 fluorine atoms, and they are tremendously electronegative atoms, and we will have 4 dipoles within this molecule. Now, this time, within the tetrahedral arrangement, these 4 dipoles are all going to cancel each other out. So even though this does have polar bonds, it will not be a polar molecule, and it will not have a permanent dipole. And so this is the correct answer. And D has got 3 electronegative atoms, and so it will have 3 polar bonds, but this bond between carbon and hydrogen is effectively non-polar and certainly will have a different polarity to the other 3, and so this does have permanent dipoles, and it will be a polar molecule. So C is the correct answer. Which change occurs when water is vaporized? Well, when you vaporize water, you start with liquid water and turn it into a vapor, a gas. And so what you start with is liquid water, H2O. What you finish with is gaseous water. The water is a gas, so H2O with a little g. And so all you've done is you've separated the particles that are in liquid water and made them be further apart to turn them into a gas. In order to do that, you need to break the forces that are between these molecules, and these are called intermolecular forces. These need to be overcome by being provided with energy. So that means that C is going to be the correct answer. A is incorrect because it actually requires energy to make this happen, so it will actually be endothermic. B is wrong because we aren't breaking any of the covalent bonds in the water itself, we're just breaking the forces between water molecules. And D is going to be definitely wrong because the molecules will have more energy once they have vaporized, because that's how they're able to overcome those intermolecular forces, by gaining energy. So C is the correct answer. Okay, that's the end of this video. I hope it was useful. I'll see you again soon.